Hello everyone, in this lecture we are going to see some concepts regarding radar. So what is the definition of the radar? Radar can be abbreviated like this: radio detection and ranging. So that is nothing but radar. Okay, so basically radar is an electromagnetic sensor for detecting the reflected objects. Okay, so what is the process involved with this one? That is what we have to understand. For example, this is the radar. Here only you have the transmitting antenna and receiving antenna. Okay, here target is available. For example, you assume that is the target. Okay, so using this transmitting antenna, some electromagnetic wave will be transmitted. That electromagnetic wave, mostly the rectangular pulses like this, will be transmitted. Okay, then this particular target will receive this electromagnetic wave, that means pulsed train. Then it will reflect back. Then these pulses will be reaching this particular receiving antenna at the radar. Okay, so because of this particular operation, we can able to understand at how much distance this target is available. Okay, and we can able to further understand with how much velocity this target is moving. That is also we can able to identify. Okay, so this is the process involved in the radar, very basic information. Now the main parts of the radar, we can see transmitting antenna, receiving antenna, and the energy detection device of the receiver. Just now in the previous slide we have seen about this one, distance calculation. So here radar is there, as we have seen in the previous slide. So here transmitting antenna and receiving antenna are available, and here some target is available. So it is sending certain amount of pulsed train, that means electromagnetic waves. So electromagnetic wave traveled the distance of r. For example, distance in between radar and the target is r. Okay, so this electromagnetic wave has been traveled at a distance of r and reaching the target. With what velocity the electromagnetic wave can travel in the free space? Light velocity c. So velocity is there, and the electromagnetic wave traveled a distance of r and reaching the target, and target reflects the electromagnetic wave. So this is the reflected electromagnetic wave, and this reflected electromagnetic wave also traveled a distance of r. Now we know that at what time we have transmitted the signal, and we know that at what time we received the signal. So the time difference between these two will give the time taken by the wave to reach the target and to come back. That means total time is available, that is t. T is equal to what we can write now? Time is equal to distance by velocity. But how much distance? Is it r? No, it is 2r, because this time is for total time for going towards the target and reaching the radar again. That means the wave has been traveled 2r distance. So distance traveled by the wave is 2r by velocity, that is c. So from this r is equal to what we can write? Ct by 2. So in this way we can calculate the range, that means the distance between radar and target. Okay, this is the basic information to calculate the distance between the target and the radar. Next, ambiguity in range measurements. Second time around echo, maximum unambiguous range. This is certain terminology we are going to use in the radars. Okay, so what is this one? We have to see. Whatever the criteria I have explained in the calculation of the distance, for that one only, this is the extension. So this is the first pulse of the transmitted signal. This is the second pulse. This is the third pulse. Like this, the series of pulses we are transmitting from the radar towards the target. Because it is looking like a periodic signal, we can define the time period for this one, that is a small t naught. So small t naught is the time period of this pulse wave. That means for every t naught seconds, the pulse will be transmitted. The pulse will be transmitted. Okay, so first pulse is generated. After t naught seconds, the second pulse is generated. So I am giving the numbering also. This is 1, this is 2, this is 3, and so on. Like this, so many number of pulses will be generated, and each pulse will be generated for every t naught seconds. Okay, so we have transmitted the first pulse. It reaches the target, because target is having the nature of the reflections, so the pulse will be reflected back. That will be received by again radar receiving antenna. Okay, if that reflected pulse is coming like this, that means with respect to time I am talking. So if this reflected pulse is reaching this particular radar after capital T seconds. Okay, but here we can give the relation between capital T and T naught. Once again I am repeating, T naught is the time period of the pulse wave, okay, which is generated by the radar. All these pulses are striking the target with the time period is equal to T naught. And whenever first pulse is reaching the target, then target is reflecting back. To reach this particular radar, it took capital T seconds. And by seeing the diagram, you can give the relation between these two. That is, T naught is from here to here, but T is from here to here only. So that capital T is less than T naught. So in this particular criteria, there is no problem for us. That means this reflected pulse, okay, I can take here 1 R. That means reflected pulse 1. That means it is related to this one. So this one we have transmitted and that one is reflected back. Okay, for that purpose it took capital T seconds. And by the completion of this capital T, the radar did not generate the second pulse. So there is no problem. First pulse has been transmitted and came back. Then we have certain time for the generation of the second pulse. So second pulse is generated. It will strike that particular target and again reflected back. So second pulse will be reaching here. Okay, this is the second reflected pulse. So there is no confusion here. We have transmitted, reflected back. Again second pulse is transmitted, reflected back before the commencement of the third pulse. Okay, before the generation of the third pulse. Okay, this first reflected pulse should come, okay, should be reached the radar before the generation of the second pulse. Okay, second reflected pulse should come before the generation of the third pulse. Like that, if it is there, then there is no problem. There is no unambiguity. Okay, sorry, there is no ambiguity. Like that we can able to take. Okay, for example, now you see, this is the first pulse we have generated. We have transmitted. It may be received by the target. We are waiting for this reflection, but it did not come. Now second pulse is also generated and it is transmitted, and now we got the reflection. Now we got the reflection. This is first one, this is second one. Now it is the reflection, but we don't know, is it first pulse reflection or for the second pulse reflection. If you consider for the first pulse, but if it is due to second pulse, and if you calculate the distance, you will get the wrong value. Okay, like that, here some confusion will be there. So in order to avoid the confusion, what we have to follow, whatever the reflected pulse is there, that should come before the generation of the next pulse. Okay, then we don't have any ambiguity. But if it is like this, then ambiguity is there in the generation of the distances. Okay, so when we don't have that one, maximum is this one. If you have the reflection at this particular place, then we don't have any confusion. This is ended, then the second pulse is generated. So how much maximum we can take here? Time is T naught. So with this T naught, if you calculate, that is a maximum unambiguous range. Okay, without any confusion, whatever the maximum range we can able to calculate is nothing but with this particular time. So like that we are taking all these things. Okay. Then radar range equation. Okay. So whatever the distance is there in between target and radar, that is what we have to get here properly, step by step we need to get. But there is a logic. If you understand that logic, easily we can able to derive this particular equation. Okay. That is what I want to tell. So here radar is there, and you assume here target is there. Okay. Wave is transmitted and reflected back. Okay. So here transmitting antenna is there. Transmitting antenna is having the radiated power, that is WR. But in the free space we are talking with respect to densities. Okay. You assume it is isotropic radiator, isotropic antenna. So in all directions it will radiate equally. In all directions means sphere we have to take. So sphere, that surface, spherical surface area is given by 4 pi r square. 4 pi, but what is the radius we have to take? We should reach the target. So the distance between these two is r. So r square. WR is the power. By 4 pi r square is there, means it is power density, watts per meter square. But we are not using isotropic antenna, practically not possible. So directional antenna only we have to use. So how to change this formula means you need to multiply with the directive gain of that practical antenna. Then no change in the units, because directive gain is not having any units. Okay. Now with this power density, we are sending the data, we are sending the electromagnetic waves towards the target. So certain amount of target area is intercepted by this particular power density. Okay. Then how much that one means sigma. So WR dg by 4 pi r square is multiplied by the cross sectional area, that is sigma. So this is area, that means till here watts per meter square multiplied with meter square, so you will get watts. You will get watts, that means this is the power. Again reflections are possible, na? So while reflecting in the free space also, again we need to work with the power density only. So this is power, but we need to convert into power density. So again you divide with 4 pi r square. So one more 4 pi r square will come into the picture. Like this we have to take. Now certain amount of area of the receiving antenna will be intercepted by this power density. Okay, that is called effective aperture area. Okay, effective aperture area is the parameter of the, or the property of the receiving antenna. So how much area is affected? That is what we have to consider. So sigma by here 4 pi square into r power 4. This one only. Now we are taking here AE. Okay. Now what we have taken in the previous case here. So you see this is watts per meter square into meter square. Again meter square is there. So this is watts per meter square. When you multiply with the again area, meter square will be cancelled. You will get watts. So this is the power. Okay. This is the power. So power received by the receiving antenna is nothing but this one. So this side I can write now, this is the radiated power, not received power. So here I am writing received power is equal to. Now from this formula, you can write equation for this R. Okay, when you will get this is the maximum, R is nothing but when the received power is minimum, because inversely related. Okay, so here I am writing the minimum power received is can be taken as S minimum, that is minimum detectable signal. The terminology is given like that. Okay, so it is equal to the same formula I am taking here. This is the radiated power, directive gain, and this is the radar cross section, and this is AE, effective aperture area, by 4 pi square into maximum R, maximum range to the power of 4. And from this you can write equation for maximum range. It is equal to radiated power dg sigma AE by 4 pi square, and by sending this minimum detectable signal power, that is S minimum. But here R power 4 is there, so if you send that one this side, you will get a power 1 by 4. So this is the radar range equation. Okay, steps are very simple. You need to work out with respect to units, and you should know about this theory. Radar itself is having transmitting antenna and receiving antenna. Transmitting antenna is transmitted certain amount of power into the space, but in the space you need to work with the power densities. So that WR by 4 pi r square, but it is for isotropic. For the practical antenna you should multiply with its directive gain dg. you are sending. Okay, that is intercepted by the certain area of this particular target, that is sigma. When you multiply with sigma, it will become power watts. Again, that is reflected. Again, in the free space, you need to work with the power density. That's why divided with the 4 pi r square. Now it become power density, watts per meter square. Again, this is received by the receiving antenna, and that is due to this AE. Okay, this is the effect aperture area of the receiving antenna. So when you multiply with AE, you will get the power. That is what we are telling, received power. Okay, and in terminology, we can able to tell minimum detectable signal power. So anyway, this is power only, just we have replaced this one with the S minimum. Then write equation for the R maximum, that's it. This is the radar range equation. Further we can modify this one, okay, by converting this DG, by changing this DG or this AE, we can write the value, we can write the equation of this particular thing in terms of the wavelength also we can write, okay. So wherever it is necessary, you can able to do that modifications. Now the next question is related to radar. Consider the following statements if the maximum range of the radar has to be doubled. Okay, so peak transmitted power. So first option is including peak transmitted power, but what we need, maximum radar range of the, okay, maximum range of the radar has to be doubled. So R must be doubled in such a way that what is to be done for the transmitted power. See here, transmitted power means this radiated power WR only. So WR, how much we have to keep in order to have this 2 times of R. Okay, what is to be done for this R for having here this radiated power? How much amount of radiated power we should have to have this? This is what they have given, 2R. This is 2R. So what is to be done for this WR? Okay, see here, 1 by 4 is there. Okay, power 1 by 4 is there. That means here we need 2, just 2. Okay, this total thing should be available with 2. Here 2 is there, means if this 2 is going inside, it will become 16. Okay, it will become 16 because here 1 by 4 is there, power 1 by 4 is there. That means if you have here 16 WR, then range will be doubled. That is what, very simple thing. Okay, so simply in this particular thing, replace WR with 16 WR and rest of the part is there, power 1 by 4 is there. So this 16 can be written as 2 power 4, 4 will be cancelled. Okay, if you apply this 1 by 4, only 2 will come outside. So 2 will come outside and rest of the part is R only, na? So 2R we will get. So simply this radiated power or whatever the peak transmitted power is there, that should be increased by 16 times. So that is what they have given. It is correct only. Okay, and it is not depending on diameter, all these things. So simply you can able to take option 1 is the correct option. Okay, thank you.